So this is the third in a series of videos on factor analysis by Dr. Jennifer Ripley at Regent University. So we're going to be talking about principal components analysis and factor analysis conceptually in this video and trying to understand a little bit of the difference between them and how they work. They're very, very similar to each other. Factor analysis is a little more restrictive. It just uses a more strict standard because it only looks at the shared variability and ignores the unique and error variance, whereas principal components analysis is inclusive of all the variance. So we talked about variance in the last slideshow that I did. So if that's confusing to you, go back and watch the video on variance. But if you include unique and error variance, it's believed that you confuse the structure set of the variables. Like that's the theory behind it. So typically people use factor analysis when they're doing scale development, not principal components analysis. But just to be aware of how things worked. So factor analysis doesn't use variance. Also, it uses covariance or shared variance. So its whole thing, factor analysis is built on a covariance matrix, whereas principal components analysis is built on a variance matrix or correlation matrix. So factor analysis produces something called factors, and principal components analysis produces something called components. They're actually calculated similarly, although one is using covariance and one using variance. But beyond that, it's all kind of going to look exactly the same. Factors cause variables, whereas components are just aggregates of variables. So you can kind of see like the stricter kind of language in factor analysis than you see in principal component analysis, which just says, well, we can describe the variables, we can aggregate the variables, and produce these components, but we can't really say much else about it than that. Whereas factor analysis says, no, we think these factors behind the scenes, like intelligence, are causing IQ scores. Things like that. We think religious commitment itself is causing answers to my RCI scale. And so that's the theoretical difference between them two. Factor analysis analyzes only the variance shared among the variables I mentioned before, so the common variance or the covariance matrix, whereas PC analyzes all the variance. A factor analysis is asking the question, what are the underlying processes that could produce these correlations? Could it be religious commitment? Could it be intelligence? Things like that. Principal components analysis is not really looking at the behind the scenes yet. It's just saying, hey, there are empirical associations here. It's data driven. Sometimes you have a study that you don't actually think there is a behind the scenes theory behind it. You're just trying to group data, and then principal components analysis would be more appropriate for that, like sociological data, census data, something like that. But most of the time when psychologists are working, we're going to be working with factor analysis because we think we're trying to measure some factor, right? Some unobservable thing. The confusing thing about PCA and FA is, this is really important that people often get confused about, is that each component or factor is not a question, right? A component or factor, remember, is this theoretical concept that represents a number of questions. However, there are as many possible or potential components or factors as questions. So it's actually possible when I create my questionnaire, I think I'm measuring one thing, but it's possible that every single question is actually measuring something different because we never really know. So part of what's happening with factor analysis is we're trying to group things together to such a degree that we can say, well, I think we're actually measuring one thing, or maybe it's 2 things or 3 things, but it's not 10 things or 50 things, right? If I have a 50 question questionnaire, we hope that we don't get 50 separate factors. We hope we can boil that down into maybe 2 or 3 factors, maybe 1. One way to help understand this is just with a metaphor. So imagine that you're in the classroom that we're in my class, or any classroom if you're watching this and you haven't been in my class. So everybody in the room has a certain distance from the instructor, from Dr. Jen, right? And everyone in the class has a certain distance from everybody else in the room or the field of data from where they're sitting. And we could give everyone in the room their own individual factor. Like I could be a factor, and every single individual person in the room could be a factor. But that would not help us reduce data, which is the entire point of factor analysis. So we want to cluster people onto islands, essentially. So we're going to set up islands that group people based on their distance from each other in our field of data, and we pull people together, and we have the back of the room island, and we have the front of the room island, and we have the left side island and the back right side island. We can do that by looking at correlations or variances, which would be a principal component analysis, or we could do that by looking at covariance scores between every pair of data, which would be a factor analysis. So some people find this as helpful to think in terms of, okay, remember, we're looking for islands which have items, questions on them, measurements of constructs on them, not looking for each individual question. Only, of course, it's not actually islands. That would make it too easy. It's calculated behind the scenes mathematically as actually a line of data. Because we are based on the general linear model still. This entire semester is the GLM, so it's a line of data. So the island is a metaphor for this line of data. So what is that here, right? Lay down the line, the best possible for the first one, and gather up as many as possible, and then lay down a second line and see if there's any left. Lay down a third line, see if there's any left, and we'll just keep doing that. So this is a quick one here. It says blue dot, but it actually turned out a little gray there. It's closer to PC2. It loads best onto PC2, but it does have a relationship with PC1. In fact, every dot on here, every X on here has a relationship with both PC2 and PC1. The distance from the line is the error score in the observation. So if everything was perfect, it would land perfectly on the lines, but it doesn't. It lands out in the field of data. So you start to see how some of the previous concepts hopefully start to pull in here. Now we have error coming in, so we have the error, and then we have the relationships of the variables with each other, and the relationship with the variables with these underlying factors. So imagine that first component, the line on our graph, which would be a number, y equals mx plus b, imagine that was able to explain 60% of the total variance of the data in a 10-question survey. This is really great. It means that component accounts for about 60%, or if data were random, 6 questions in the survey could be answered on that. So perhaps the next biggest component will add about 25% more, right? So this would be if the x's, 25% of x's essentially fall close to that second line. And now with just 2, we're explaining 85%. Well, maybe we want to add a third one, and that third one gives us 10% more. We're now up to 95% of the possible variance. Wow, that pretty much never happens, by the way. I just use this as an example. That's a really high percent. But the implication is that 3 questions, those that are closest to those 3 components, can give you 95% of the capture of the construct. So we could actually just ask 3 questions instead of 10, because those questions that are underlying, that are representative of those constructs are capturing 95% of the variance. And if our goal is parsimony, our goal is to try to boil down the number of things we measure from 10 to be a smaller number, then that's great. We would love to have 3 questions that can nicely measure something. Great. Here, then, the eigenvalue is the line plot, and you look for, when you keep adding them, when do you stop adding significant percentages of variance in explanation, and also in Kaiser's rule and eigenvalues, that we need at least like an eigenvalue of 1. And you'll see later, eigenvalue of 1 is a pretty good number. So, all right, so hopefully this gives you some conceptual behind the scenes explanations. I know it's kind of a matrix of understanding. You might have to go back over some of this material as you get more familiar with the concepts.